Hello everyone, welcome to the March 26th lecture for Calc 2. Quick reminders, your web assign is due Friday, and you should continue submitting your course notes each day. So, I'll do a little recap from last time. Last time we looked at the polynomial f of x is the square root of x, and we found the Taylor series around c equals 4, that's the value that we centered at, the x value. And we found that the degree 2 Taylor series, or Taylor polynomial, is 2 plus 1/4 x minus 4 minus 1 over 64 times x minus 4 squared. So if you look at the graphs, you will see that I have the point 4,2, that's the green point. That's where we create our Taylor polynomial from. And you see that the red curve is the square root function, and the blue curve is our polynomial. And you see it's very close to the actual square root function if you graph it. So let's do an approximation and show you how close these numbers actually are. So let's say we want to approximate the square root of 4.1. Well, we see that this should be roughly equal to P2 of 4.1. And if we compute P2 of 4.1, that's where you plug in 4.1 for x. You will get the number roughly 2.024844. And the actual value of the square root is equal to 2.024846. That's really close. We got the first 5 decimal points right by using a degree 2 approximation. So that's wonderful, but how do we know how close we are? So for example, you used your approximation to compute this number right here. Your computer calculated the number I'm pointing to in blue. However, how did your calculator know that was the right answer? That is what we're going to talk about now with the remainder of a Taylor polynomial. So there's a theorem that's going to tell us how close are we. So we have to introduce the concept of a remainder. And you'll see why it's called a remainder very soon in a couple lectures. So if I have my function f that I'm approximating by a polynomial p of n, the remainder is simply equal to my function f minus my polynomial. The remainder is how far off am I? We might call it the error. All right, so it's not exactly the error. The actual error is the absolute value of the remainder, which is the absolute value of this difference right here. Okay, so what do we know so far? So far, we have shown that f of x is our polynomial Pn of x plus some remainder. And I know what this polynomial is from last time. It's the degree n Taylor polynomial. All right, that's a lot of work. So the theorem tells us this. Our theorem, which we're going to call our remainder theorem, tells us that the size of my error is less than or equal to x minus c raised to the n plus 1 power over n plus 1 factorial times the maximum of the n plus 1 derivative at some number z, where z is between x and c. So we think of x as a value, and our remainder is less than or equal to this kind of complicated looking expression on the right. This is the important expression to know about the remainder. Okay. So let's do an example for a function we all know and love, the cosine, because this will tell you how we actually calculate values of the cosine using techniques a bit like this. All right, so we have the cosine function, and we're going to expand it around c equals 0. And I want you to pause the video and calculate the degree 4 Taylor polynomial of the cosine about c equals 0. So pause the video and go ahead and calculate that. All right, now you've had a chance to calculate it, you probably got something along the following lines. All right. So let's just approximate the cosine. So let's approximate the cosine of 0.3, and we know this will be roughly equal to P4 of 0.3, which is equal to well, we just plug 0.3 into the expression, 1 minus 0.3 squared over 2 factorial plus 0.3 to the 4th over 4 factorial. All right, that's our approximation for the cosine of 0.3. How close are we? Well, we can use the remainder theorem to tell us this. So we know that our error, or our remainder, for this value, so that is if we plug in 0.3, is less than or equal to 0.3 minus c, which is 0, to the n plus 1, so that's 4 plus 1, over 4 plus 1 factorial times the max of fn. So we know that f of x is the cosine, f prime of x is the negative sign, and so f, the fifth derivative, is the cosine, excuse me, it's the cosine. So this is the max of sorry, my mistake. I was right the first time. This is the negative sign. Okay, so this is times the maximum of the absolute value of the negative sign of z, where z is some number between 0 and 0.3. You see, this is c, this is x, c, x, and this is n. N is 4 in this case. It's the degree of the polynomial you're using. Okay, well, what do we know about the maximum value of the sign? We know this is always less than or equal to 1. So what we can do is we can continue our inequality, and we get this is just less than or equal to 0.3 raised to the 5th power over 5 factorial, which is about let's see, 1, 2, 3, 4, 4 zeros, 2025. So this tells us that our error is less than this number right here. Wow, that's small. It means that our approximation is accurate to 4 decimal places. That's pretty great. Okay, so what this tells us is that we can approximate our function values to very high precision, and this theorem tells us exactly how accurate we are. So, last but not least, when you are calculating, let's say you need to estimate something to within 1/100th, you want to know how many terms of your Taylor polynomial do we need. So this brings up another question for us to address, is sometimes we want to find the degree of the polynomial, in this case the Maclaurin polynomial, required for the error in our approximation of f of x equals e of x to be less than 0.001 when estimating f of 0.6. Okay, so we want to know how many terms of our Taylor polynomial do we need to be accurate within 1/1000 when we're talking about the exponential function. Okay, so what do we know? We know that f of x is e to the x, f prime of x is e to the x, and in fact, every derivative is equal to e to the x. That's helpful. So what it tells us is that our error is equal to the n plus first derivative times x minus c to the n plus 1. We don't know what n is going to be, so we need to figure it out. So this becomes e to the z over n plus 1 factorial times 0.3 to the n plus 1. See, we know that c is 0 because this is a Maclaurin polynomial, and x is 0.6. Okay, so we're going to create a table of values to figure out what n we need. So we know that on this left-hand side, over here on the left that I'm writing, this expression is what we need to get to be less than 0.001. So let's make a table and figure out what's the first n that works. Okay, so we have n, and we have e to the 0.6 over n plus 1 factorial times 0.6 to the n plus 1. Okay, so if n is 1, I can plug it into the calculator and I get 0.328. For 2, I get 0.066. For 3, I get 0.0098. For 4, I get 0.00118, which is very close, but not quite. And then I have 5, which is 0.00012, roughly. And so here we have a winner. So what this tells us is we need P5 of 0.6 to approximate e to the 0.6 within 1/1000th. All right, so you'll see these problems on the homework where it will ask you, I want my Taylor polynomial to approximate this function value to within a certain amount of precision, and you have to find that n. All right, let me know if you have any questions, and enjoy the weekend.